Hey guys, it's Josh Myers, and I'm back, and I'm bringing you the second part of the hybridization theory section of this channel, Academia on Demand. Okay, so in the first video, we were introduced to the idea of hybridization and the idea of electron promotion. Electron promotion, and how this enables atoms to free up orbitals to pair electrons in bonding. So pairing of electrons in which one electron is donated from one species and one electron is donated from the other species. Most of the time, at least. And we know the exception would be dative bonding here, but we will leave this as a rule for right now. Start, actually. Okay, so and the second thing that we learned was that in hybridization, the orbitals that participate in bonding are of the same energy. So the orbitals, no. I need to be more clear, use less words, okay. So, no. Bonding orbitals possess the same energy. And this really makes sense because this is how molecules become as stable as possible. And so, for example, if we were talking about, as in the last video, I gave the example of methane. So when CH4, when carbon bonds with these four hydrogens in its tetrahedral 109.5 degree shape, we have the idea of the electron promotion, but then the creation of the sp3 hybrid orbital, in which there are four orbitals that can participate in bonding. They are all half-filled, but most importantly, that they all have the same, so they have equal energies, and in fact, they are actually, as we showed in the last video, they are a combination of the 2s and 2p orbital energies, which means that they are right in the middle, which makes sense because it is a combination of one s orbital and three 2p orbitals. Okay, and so that is another one of the big rules that we learned in the last video. And then finally, the last big rule, we are starring them. In the last video, we talked about it right at the end with boron and aluminium, where the atoms within the same family, so atoms within the same group, I keep calling it family, we're all family here on Earth, but these atoms are in a group. Atoms in a group have the same bonding behaviors. And this is because of the hybridization of the electrons is common within the group, because all atoms down a group have the same number of electrons. So atoms in a group have the same bonding tendencies. And you can see I've switched to my blue marker here. I haven't used this one in a long time. Bonding tendencies. Now that I've gotten my new board that erases nicely and doesn't give me problems, I can use this thing. Alright, and so now those are the three big rules that we learned in the last video. And now what we will be doing in this video is learning more about the specifics of how molecular orbitals are created beyond just simply the electron promotion. Because as we know, we've learned that the electron is promoted, and this creates orbitals that are of equal energy for bonding, and it also creates half-filled orbitals so that electrons in the bonding can be paired. Okay, so, but it does not tell us exactly how the pairing happens, exactly how in physical space a representation in our minds of how this happens. So the first thing we need to do in order to discover how these molecular orbitals, how this idea from Vesper can be applied to hybridization, is we are introduced to two different kinds of molecular orbitals. And these kinds are called sigma, and we can almost say they are bonds. Sigma bonds, and the symbol for this is actually the nice sigma symbol. And then there are pi bonds, and I'm going to leave a little bit of room. Pi bonds. They have different properties that make different things happen. Okay. See if I can draw my pi symbol. I tried. Okay. So what are the characteristics of sigma bonds? What are the characteristics of pi bonds? What is the difference? So the biggest difference is that sigma bonds overlap head-on. So they overlap, and I'm using this super important word overlap because it is the professional word. I'd like to call it the right word here when we're talking about the creation of molecular orbitals, because the creation of molecular orbitals is the blending or overlap of atomic orbitals. And that is the new way I want you to think about this. So the overlap of hybrid orbitals, as we know, hybrid orbitals are the ones that participate in bonding. Hybrid orbitals, and the overlap of hybrid orbitals head-on. And when I say head-on, what I mean is if we have the, let's go back to the methane example, we've got our CH bond right here. And in this bond, what has happened is it is a hybrid orbital of the carbon overlapping with now the orbital of the hydrogen. And so the way this has happened, if we're looking even at just this shape, so if we're, say, let's just draw out a p orbital for a second, even though we know technically hybrid orbitals sort of have their own shape, let's just pretend for a second that it's one of the p carbon orbitals bonding with one of the s hydrogen orbitals. This overlap, this idea of overlapping to create this molecular orbital, because as we know this is atomic, and atomic. This overlap creates the new shape, the new molecular orbital of, wait for it, so we got our normal p, but then this one gets really big. It's much bigger than the other side, because this is the representation of this s orbital, this sort of circular shape being added to this sort of dumbbell shape, and then we have this resultant molecular orbital that is of this shape. That's how you want to think about it in terms of overlapping. Such an important word right there. Okay, and so that is the idea of overlapping, and that CH bond is indeed a sigma bond. So now, how does this influence different characteristics about the bond? Well, as we know, as we've said before, it's a hybrid. It's the overlap of hybrid orbitals, in which actually pi bonds, you find out they're only the overlap of atomic orbitals, which is a little bit funky, but we'll see exactly how that works. But the biggest idea that I want you to grasp when distinguishing between sigma and pi beyond the head-on overlap versus what we'll find out later about pi bonds, is the sideways overlap in pi bonds, is the idea that sigma bonds, let's make this over here actually, sigma bonds create areas of electron density, so areas of, shoot, that's electron. Oh my gosh, I am not talking what I'm doing right now. Okay, so areas of electron density, are created on the plane between the two nuclei. And what this means exactly, the two nuclei. This means that when this CH bond is formed, let me fix this. When the CH bond is formed, CH, the molecular orbital that is created will always keep the electrons that are possessed within it on the plane between the hydrogen and the carbon. So if we draw out, let's say this is the nucleus of the carbon, that's carbon, and this is the nucleus of the hydrogen. And obviously that's not, there's more protons than that in carbon, but let's just pretend for now this is what it looks like. And we've got our molecular orbital, so we've got our this, and then our big ball, because as we know it's an S combined with a P, if we're looking at it that way. And somewhere in here, somewhere in this area, the electrons are most likely to be found. And so sigma bonds, the areas of electron density, so the areas where the electrons will be found, are on the plane between the two nuclei, which means that they are on this plane, which means that they aren't above, they aren't below, they are right directly on the plane of what you'd say almost the bond. If we're talking about the straight line here, they are right on this straight line. Okay, so now we are going to look at pi bonds, and then look at exactly where they appear in different molecules. And then we will examine more characteristics. We'll figure it out as we go. Okay, and so pi bonds, and I'm going to run through this pretty quick. They overlap, very important word again. They overlap, but this time that they overlap atomic orbitals. So overlap of atomic orbitals sideways on. And you're going to say, how the heck could that happen? Orbitals sideways on. Alright, now I'm going to tell you exactly how this happens. Because pi bonds can only take place, they can only be present in areas of electron density, so in bonding areas or in lone pair areas where there are double bonds or triple bonds, when there are more than just single bonds. So if we look at the single molecule of N2, so if we have our N, we've got our lone pair, we've got triple bond, and then another N, and then a lone pair. And we look at these three bonds and we say, are they pi? Are they sigma? How do we know? So the first one, the first single bond, so anytime something is singly bonded, it will be a sigma bond. It will be on the line, the electrons will be on the line between the two nuclei of the bonding atoms. But then these other two orbitals, so if we've drawn this out, and let's just pretend that it's two, this is the sigma, let's do sigma, but then the other two bonds will be pi bonds, as I've said. And so in pi bonds are always the overlap of atomic p orbitals. So we can almost label this p orbitals. And so what ends up happening here is actually, if we were to draw this p orbital sort of thing, and we are to draw another n here and a p orbital here, they overlap, they link sideways on, which what really ends up happening here, what this would look like from this picture, is it would almost create an orbital that has a little bit of a box shape. It's a little bit of a box shape, in addition to this sigma bond, where we're going to use this straight line. But then this second pi bond, because this second p orbital, it's going to have more of a setup of, they're going to be leaned more this way, because as we know, the p orbitals are vertical, horizontal, and diagonal. This second pi bond is going to be lined up like this, and it's going to create a sort of shape a little bit like this. And so then the second one will have a shape a little bit like this, and they will all sort of be in this same area. But the biggest distinction, where as far as the electrons are concerned, besides the idea that it's atomic orbitals, so not hybrid orbitals, but atomic orbitals, but the biggest distinction is the idea that the areas of electron, let's do a short form, let's go density, use a big D for density, electron density, are created above and below the plane, above and plus below the plane of the two nuclei. Plane the two nuclei. So, oh no, I think I moved you. Are you okay? Oh no, okay, just hold on for a second. I moved you back. You're good. Alright, so, and we understand this, so what this means, this idea of electron density being above and below the plane, is that literally if we have, let's erase this for a second, we understand how they're shaped now. If we have this plane, this nitrogen nucleuses, and we've got this plane right here, this is right in the middle of the plane, the electron density, where the electrons are in this molecular pi bond, molecular orbital, pi molecular orbital, they are above and below the plane. And this is actually super significant because it actually, to a certain extent, affects the elements that bond with it. Because elements that enjoy accepting electrons a lot will actually be attracted to molecules that have this sort of electron density above and below the plane, because it doesn't have to get as close to the molecule to be attracted to these electrons, because they are literally coming off of the molecules, you'd say. They are above and below, as I've said many times. And these molecules, these reactive things that like these electrons, they are called electrophiles. Electrophiles. And we will learn a lot more about them in organic chemistry. Electrophiles. And we are going to cloud that up for a total of not a very long time, because now we have to erase. So maybe we'll leave that. Okay, we'll erase the top. And so how does this affect certain things? How does this affect certain things when bonding? So if we're talking about the idea of molecular geometry, how is it that these things interact? Because as we know, sigma is always the first bond, pi is always the second bond. Second, third, fourth, however many bonds. But more characteristics about these things. So sigma bonds, as we know, they are hybrid orbitals. So hybrid orbitals. But a big distinction, we'd say trademark almost, of hybrid orbitals is the idea that they are the ones that participate in repulsion. So they participate in repulsion. And when they participate in repulsion, when something participates in repulsion, it also influences the molecular geometry. The molecules, it owns its geometry, because we have a apostrophe there, and that is ownership. Molecules geometry, which means that the sigma bonds are the only ones, yes, that influence this geometry. And this has a lot of implications, actually, because what this means is that sigma bonds, they do not only include bonding in itself, because the idea of hybrid orbitals can actually be single bonds. They can be single bonds or lone pairs. And this is where it actually gets interesting, because hybrid orbitals don't only have to be bonds. They can be lone pairs. So single bonds or lone pairs. And so this really comes in handy, because we get the idea that when we are doing the hybridization of different things, and now I will erase this. The molecular geometry, which is determined by the hybridization of the number of orbitals. So if it's sp2, we are going to say it's trigonoplanar. If it's sp3, it's going to be tetrahedral or some other thing of this such. If it's, maybe bent tetrahedral, or if it's trigonal pyramidal. If it's one of these things, then we say it's sp3. But what if we were to relate this to how sigma and pi bonds appear in molecules? Let's say that, let's talk about the organic molecule ethane. Ethene at C2H4, and this is ethene. And so if we draw out this molecule, we've got our carbons connected to each other, and this is a big factor. This is a big theme in organic chemistry, drawing these molecules, these carbon-hydrogen molecules only. But what we will look at here is the idea that we know from earlier videos that the molecular geometry is largely determined by the number of areas of electron density around a central atom. So here, carbon. There are three areas of electron density. There are 3 areas of electron density around this central carbon. And so therefore we would say it has a trigonal planar geometry. So trigonal planar geometry. But what can we deduce about the sigma bonds and pi bonds here? So we know that there are three sigma bonds always that are going to surround this carbon, because we know it's bonded to 3 things, and always single bonds, the first bonds that something reaches out to something else and decides, let's bond, we're having fun, we want to be energetically stable, they are always going to be sigma bonds. And so there are three sigma bonds here. But this double bond, once you have the presence of this double bond, you get the pi bond. So you get the pi bond. And this is exactly how we've talked about it before, that the double bond now is represented by a pi bond. But what does this mean in terms of the idea of the geometry? Well, because usually, other than in the cases that we've talked about before, of boron and fluorine and those group 3 elements, usually when something has 3 areas of electron density around it, and it is stable, so it has 8 electrons around it, it will have a double bond. So this means that when something is sp2 hybridized, it is very common that it has 3 sigma bonds and 1 pi bond, and that therefore it can be susceptible to those things that we call electrophiles. And that's actually exactly how this ethene molecule can bond to things like bromine and create a situation in which bromine will bond here and here because of its attraction to these electrons that are above and below the plane. Okay, so it just looks like we're just about out of time, but in the next video we will go into many more examples of exactly how this theory can be applied all together, because now we know the molecular part of it. We just talked about exactly how these sigma and pi things, how this all fits together in our picture of what molecular geometry is and what bonding is. And so now we have a deeper understanding of that. We will talk more about these examples in the next videos. See you guys.